We are going to talk about electrostatic potential energy. Extremely important concept from the energy viewpoint, how we are going to have an expression, how we are going to relate few quantities, and we'll try to understand about electrostatic potential energy and electrostatic potential. Well, when we talk of forces, right? When we talk of forces, when we are talking of electrostatic force, that is the Coulomb's force, what kind of force is it? It's a conservative force. And if you recall the concept of conservative force, what we recall about, what we collect those essential concepts when we talk of conservative force, how can we determine, how can we identify a force to be a conservative? So if you remember, in case of conservative force, the force which is responsible for the work done, so the work done by the force, if it is path independent, that essentially means if you calculate the work done by the force, wherein it just depends upon the position of the initial and the final position, and it is independent of the path taken, then such forces are called conservative force. Or in other words, if you calculate the work done in a closed path, work done by the conservative force, then if you remember, the work done by the conservative force, if you take into account, suppose F is 4 and you operate the work done concept, which is a dot product, right? A scalar product. And this is showing you the infinitesimal small displacement happening. In a closed path, if you're going to calculate, and this force happens to be a conservative force, then the work done is going to be 0. Either of the two situations, if you find that this is where the case is, the force involved is path independent, or the force here, if you calculate the work done by the force in a closed path is 0, then you say that that force we are talking of is a conservative force. Now, what exactly, how intuitively we understand about it? So if you talk of in the context of electric charge, that is stationary charge, it creates an area of influence. So it's an area of influence, it's a condition of a space that is created because of the stationary charge. And that is, there is that field is exerting force if you bring any test charge. So that field is because of a source charge, and the area of influence is that field that we are talking about, and you bring any other small charge there, same with this, of the same nature, then it's going to feel a force, and that is a repulsive force. Why? Because it's same nature. So in this context, we talk about that there is an area of influence, there's a condition in the space. Quite similar to gravitational concept, right? A gravitational force, if we talk about, there also we do have a condition in the space, and we know that from our understanding of Newton's gravitational law that says that if the masses are m1 and m2, then the product of masses over r square, this we get as a force of gravity, the relation. So this force of gravity is inversely related in this way. It's an inverse square law. Similarly, in case of Coulomb's law, that is electrostatic force, if you remember, we do have a K and as a constant, electrostatic constant. And if there are two charges, we do have this expression, if you remember, this force, it's also holding true the inverse square law. It's also following the same. So it's quite similar. The one point which is not similar is this gravitational force is always attractive, whereas this electrostatic force could be either repulsive or it could be attractive, both ways. However, the nature, if you figure it out and you draw the analogy, both follows inverse square law. So there's a bit of this. So these two, both the forces are conservative force. Here also, if you find the potential energy, right? You would find the potential energy as a function of position because of this. Here also we'll figure it out how it depends upon. So it depends upon the position as well. It is depending upon just in R, right? Which is the separation between the charges. Similarly, conservative force, if you look into the nature, the spring force is also a conservative force. The celestial body, the gravitational force that exists between the celestial body, that's also a conservative force. Well, having understood about conservative force, we'll try to now figure it out what exactly could be the relation. The relation in the sense, when you have this concept of conservative force, then what's the relation between the potential energy? So with conservative force, what's associated is the potential energy associated with the conservative force. If you take this into account and you try to figure out what's the relation then between the work done and the conservative force involved, that is, a potential energy is involved, what's the relation between these two quantities? So we'll try to figure it out from a concept wherein we know that energy, and we are talking of potential and kinetic. So suppose this energy we are talking about is the mechanical energy, right? The mechanical energy is conserved. So that essentially means that this mechanical energy is sum of kinetic energy and sum of potential energy. If you want to express in an equation, we can write sum of kinetic and potential energy. The general notation which is used for the energy is equal to the energy. Now, if you want to take the difference of it, the difference, that is, in differential form, if there is a change in kinetic energy, suppose we denote this by dk, differential change in kinetic energy, plus change in potential energy, right? Change in potential energy. This should be equal to 0. Why? There's no change in energy. Why? Because energy is constant. Energy is constant. So if you take the differential form, there should not be any change. Or in another notation, you can write in this way: delta K plus delta U should be equal to 0. From work energy theorem, if you recall, right, this change in kinetic energy is what? It's work done, right? It's work done. So if you want to find what's the work done, and suppose just one conservative force is into picture, now this work done plus delta U should be 0. Therefore, we get a very important relation, that is, this delta U is coming to be negative of the work done, or work done is negative of change in potential energy. Extremely important concept here. So if one conservative force is there, we are talking about, then we get a very interesting relation. If you go in sequence to relate with the work done, we get the work done by the conservative force. Here we have a conservative force as electrostatic field. So work done by electrostatic field is equal to negative of delta U. So what does it mean? It means that this work done results in the decrease of potential energy. So the work done by the conservative force results in the decrease in potential energy. Decrease in potential energy. This is what it means. So now here comes the question. There's a condition in the space and energy is conserved and you are changing the position. So what would happen? Suppose you are changing the position, means you want to change the position, so there has to be an external force. So where this external force that you're applying is stored as, or where it is going, where it is getting transferred, right? So this energy and work, actually energy and work, these are like transferring. Work, energy, it is transferring. So the work that you do, providing the external force, in the context of, in the condition of where the conservative force is acting, question comes where this external force is going. It's actually getting stored in the form of potential energy. So in the presence of conservative field, when external force is done against, and the work is done against the conservative force, then there is increase in potential energy. So that external force is getting stored up as a potential energy. But when we take into consideration the work done by the conservative field itself, which means that now the force acting, if you consider, done by, the force acting is the conservative force, and the work is done by the conservative force, not the external force, then there is a decrease in potential energy. Extremely connecting concepts that we need to, before we move on to have an expression, we need to know these essentials about how the quantities are related. I have a charge here. Here we have a positive charge, and this we denote by capital Q, and we term this as source charge. Why? Because of this charge, there is a field there created, a stationary charge. And somewhere here, at any point, suppose we take a finite distance. Suppose we take a point here, and from A, we want to reach to this point P, and we want to bring this charge, small charge, which is again a positive charge, and we'll call this charge as a test charge. We'll call this as a test charge, means that this is of significantly low magnitude and it's not going to influence the electric field of this, but it's a charge, and there's the value small q. Now the path that's going to be here is this path, right? This path. So from A to P, we want to bring from A to P this charge. So what we need to do, we need to exert a force, and we call this force as external force F. What we'll keep into mind, that this external force is actually exactly balancing the electrostatic repulsive force. So this plus Q charge is going to push this to this direction. Both are positive. So there is a Coulomb's force acting, it's pushing, and we call this Fe. And this external force is exactly equal to Fe, but in the opposite direction, obviously. So this condition would lead us to, there would be no acceleration, right? There would be no acceleration in this situation if we have both the forces equal in magnitude but opposite in direction. So very slowly we are going to bring this from A to P. Now what could we have as a work done? If I want to write an expression for the work done, we can have work done by the external force, that is we can write it here, F external. This we can write from where to where? We can write from A to P, it's going A to P, and we have what? The force, which is external force, dot, and suppose we take dr as differential displacement in this direction from A to P. So this should be equal to, if you want to write in terms of this, we'll have to have a negative sign, and from A to P we are getting this expression that it should be Fe dot dr. Well, this is what we get as a relation. This is the work done, right? So the work done is going to be F work done by the external force is equal to negative of this expression. Okay, having understood this, now can we define the potential energy? We can define the potential energy as, because this one is related to the potential energy, that this force work done by the external force in bringing a charge from one point to another is the it would result in the change in potential energy. There would be a potential energy, some potential energy of value here. Suppose here the potential energy value was UA, here the potential energy value is UP. So therefore difference of potential electrostatic potential energy between these 2 points would be potential energy final, which will be UP minus UA. This is going to be the change in potential energy, and this change in potential energy is equal to this. This is what we get at first instance, a concept. Well, now there's something more to it. Suppose here we have taken A, and instead of A, we can take any position, right? We can take any position, because this potential energy is only depending upon the positions. We have taken a finite potential value, potential energy at A as UA. What if I bring this from infinity instead of this? If we bring this from infinity, and at infinity we can conveniently consider the potential energy to be 0, too far, right? Potential energy at infinity to be 0. So our equation here would be modified this with infinity. So potential energy at infinity is going to be 0. So we can write just change in potential energy. It would be just what we have the potential energy at this point. So from here, the concept of electrostatic potential energy, that is potential energy of a charge at a point, is defined in that ways. So if from this concept we would define now what would be the potential energy, what would be the potential energy of a charge at a point. So definition of electrical or potential energy, just write potential energy, suppose potential energy of a charge at a point. How do we define that with this concept? So we can define this as, having understood the mathematical expression, let's in words we'll define that the work done, so this could be defined as the work done by the external force on the charge. And where is this charge? This charge is, which is placed in the electric field. The work done by the external force on the charge in bringing from infinity to that point in the field. So we can define this that work potential energy of a charge at a point could be defined as the work done by the external force on the charge. Now here we just need to remember this external force is exactly equal to the electrostatic force, equal in magnitude, opposite in direction, so that there is no acceleration. So that point has to be noted here clearly when we talk of external force. So the work done by the external force on the charge, which is placed in the electric field in bringing from infinity to that point in the field. Simply, it could be defined in these words. So the external force here, we have already mentioned here, this external force should be equal to, in terms of magnitude, exactly equal to the electrostatic force, and should be in direction opposite to this. So that is how we define potential energy of a charge at a point. Well, now after having understood this definition, we'll try to now figure out what expression we get when we have configuration of charge, that is electrical potential energy of configuration of charges, So let me rub this and we'll proceed to derive a mathematical expression taking quantities here. So take down this, try to comprehend each keywords in this definition, and then with the same concept we are going to now understand that what would be the electrical potential energy of a configuration of charges. So having understood what electrostatic potential energy means by this definition, we now go a step ahead to find potential energy of configuration of charges. So we'll take a situation of two, let's take an example of 2 point charges. 2 point charges. 2 point charges Q1 and Q2 are taken in this example to understand what expression we get. Well, I'll rub this part and then we'll try to understand what was initial situation, what was final situation, and then what we get as a potential energy. So from 2 point charges, if we begin our discussion, so suppose one charge is Q1 here and we have Q2 here. So this is initial state. This is initial state. By 2 point configuration, we mean two charges are there, and suppose the separation is R1 initially. Now, when we apply the external force, there is a change of state, and now we are into final state, and now suppose the separation is R2. Now suppose the separation is R2. So this is a final state. So in this transition of a state, initial state and final state, if we apply the concept of potential energy, what do we get finally? What expression do we get? Now we are taking into consideration, suppose Q1 is here and we have here Q2. Q2 is here, and now in this same direction we are increasing the space, and we denote this by infinitesimal small change in the distance would be r. So initially this is r, right? And we consider this to be dr, and then we will integrate from r1 to r2. So if you want to write an expression here for the work done, so we know the work done, the external force, both are positive, right? So here we are taking both are positive, so Fe would be repulsive in this direction, and the dr is also in that direction. So therefore we can write what is the work done by the electrostatic force or the electrostatic field is going to be integral r1 to r2 F dot dr. We can write this, and we can have this F dr cos 0, which is F dr would be the equation, the dot product result of this work done. So work done is going to be this, and this is Fe. Well, so this is equal to, if you operate the dot product, it would be magnitude of Fe and dr is there, and then we have cos 0 is 1, so it remains as it is. All right, so we know what is Fe, magnitude of Fe, right? So magnitude of Fe is 1 over 4 pi epsilon naught q1 q2 divided by r squared. So we have this equation that we have here, r1 to r2. So we want to find what is the net work done. So net work done, we got this Fe, magnitude of this, magnitude of the infinitesimal small displacement, and cos 0. So this comes out to be We is equal to magnitude of Fe, right? So we know that that is Coulomb force, which is 1 over 4 pi epsilon naught q1 q2 over r squared. So we need to integrate with these limits, and we have here this. So whatever is constant we'll take out of the integral sign, so we'll get work done is equal to 1 over 4 pi epsilon naught, and we'll have q1 q2 also taken out, and then we have here r1 r2, and we are left with 1 over r square dr. So if we integrate 1 over r square, we know it's going to be minus 1 by r. So we get here work done by the electric field is equal to minus, so we'll keep it out of the sign here, and it comes out to be 4 pi epsilon naught in the denominator, and we have here 1 over r square, and we'll put r1 and r2 as the limits, lower limit and upper limit. We'll evaluate this, we have evaluated this definite integral, and we've got this, and so now we get finally We is equal to minus of q1 q2 by 4 pi epsilon naught, and then we have here 1 over r2 minus 1 over r1. This is what we get. All right, so we know that the change in potential energy, right? So this work done is equal to work done by the electrostatic force is equal to negative of delta U, which means that the work done by the electric field results in decrease in potential energy. So if you want to figure out what is delta U, which is change in potential energy, that is the operation here, what was the potential energy at, suppose R2 is the final, R1 is the initial. So we are going to find this here, which is negative of this, which means that therefore delta U is going to be negative of minus q1 q2 by 4 pi epsilon naught, and here we have here 1 over R2 minus 1 by R1. So this is how we get negative will become positive. So therefore, delta U is equal to Q1 Q2 by 4 pi epsilon naught, and here we get 1 over R2 minus 1 over R1. So now this delta U, can we write this delta U? So I'm just separating the two derivation parts in this way. So this delta U could be written as U2 minus U1 from here, that is final potential energy at this position minus potential energy at this position. And we know this, at R1, what was the potential energy? It was 0, right? If we consider R1 is at infinity, then UR1, the potential at this position, is equal to 0, and UR2, let us generalize that, the final one, as UR. So we can write therefore U at any position R is equal to, and suppose we take UR2 as equal to U. So these are few assumptions that if we take here, so we'll get the potential energy expression as this comes out to be 0, then 1 R1 is infinity, which means that 1 by infinity, it comes out to be 0. So we are left with 1 over 4 pi epsilon naught Q1 Q2 by R in the denominator. This is the expression that we get for the potential energy in terms of whatever we have the values of Q1, Q2, and the R will substitute. We already know what the constant 1 over 4 pi epsilon naught is, and we can evaluate at any point P. At any point P. So there's a general equation that we get for the potential energy. So extremely important derivation. Go step by step as we get to this result. And in the next video, we are going to talk about electrostatic potential. So what's that, and how we apply this concept to the given information, and then we'll move on to solve few questions, numericals. So watch the next video, don't miss it out. Thank you.